Thank you so much, Lauren. So I'm going to talk a little bit about how we detect light through our eyes and how we can observe the world around us. So the first thing I want you to notice is this night sky. We can see many things in it. We can see the stars, we can see the Milky Way, we can even see some trees in the distance here. Our eyes observe things around us and allow us to make observations about our world. But what exactly are we observing? We're observing light. So let's look into how light is formed in our universe. Let's start with the sun. The sun is a huge star in our solar system, and inside our sun is a core. Inside this core, lots of reactions are happening. And as these reactions happen, small photons are actually formed. This little bitty dot right here is a photon. It will bounce around inside the sun for a long, long time until it finally reaches the edge of our sun. Once it reaches the edge of the sun, it will zoom out into space, into the vacuum of space, and will head in a relatively straight line. So from our sun, these photons are zooming out, and they're actually zooming out in all sorts of directions. Equal distance from our sun, coming out in every single direction. Every once in a while, some of these photons actually reach our Earth, located right here. Even though that distance is so expansive and so long, it only takes about 8 minutes for a single photon to go from our sun to our Earth. It travels that huge distance in such a short amount of time because our photons are traveling at the speed of light, very, very fast. So you might be asking, what exactly is a photon? I'm going to use this cartoon right here to help illustrate what a photon is. It says, a photon checks into a hotel and is asked if he needs any help with his luggage. The punchline is, no, I'm traveling light. So basically, you can think of photons as traveling light particles. And we can actually take these photons and characterize them, first by their wavelength. So you might be asking, what is a wavelength? What does that even mean? We can classify wavelengths based on the distance between one peak to the next. For instance, short wavelengths will have a very short distance from the top of one peak to the top of the next peak, whereas long wavelengths will have a longer distance between those two peaks. So we can classify photons based on their wavelength. We can also classify them based on the color, and this is actually correlated with its wavelength idea. So in this fun little video here, I have a red hexagon, and it's jumping. And you notice that it takes longer for it to go from one jump to the next. This would classify as a long wavelength. Whereas our little blue ball here is jumping very rapidly. He has a very short wavelength. So you can remember that photons can be also classified on their color based on the length of their wavelength. So red will have a long wavelength, whereas blue will have a short wavelength. These particles of lights can also be classified by their energy. As they're traveling along, they're traveling at the same speed. You notice that regardless of the wavelengths that we're talking about here, they are traveling at the same speed. So we can actually also classify these photons based on their energy. So if you can imagine our red photon right here, he's kind of lumbering along. You can imagine him as being maybe an older dog. As he is walking along very, very slowly, he has low energy. Whereas our small blue photon here can maybe be a small puppy, and he has a lot of energy, and is jumping around a lot. So we can classify also our photons based on their energy as well. So red photons with long wavelength would have low energy. They would be our older dogs. Whereas our blue photons with their short wavelength would have very high energy and would be our puppies with lots of energy bouncing along. So what scientists do is they actually take photons based on all their different types of wavelength, and they classify them in a special tool called the Electromagnetic Spectrum, which is basically a chart that takes photons and puts them in a row based on the wavelength that they exhibit. So for instance, we have radio waves, which is similar to what we hear in our car stereos, to microwaves, to visible photons, which is what is emitted from our sun, to X-rays, and finally to gamma rays, which is what infamously turned Bruce Banner into the Incredible Hulk, but is also is exhibited in many radioactive substances. And they classify these photons based on their wavelength. So for instance, radio waves have a much longer wavelength, whereas gamma rays have a much shorter wavelength. And you notice in the middle here is our visible light spectrum. So how long is long and how short is short? So the long is on the scale of mountains. These have really, really big wavelengths, whereas short is on the scale of atomic nuclei, very, very small pieces of our universe, which Kimmy will describe in a little short while. But let's focus in on this visible light spectrum part right here. If we were to zoom in on that part, we'll see actually the full rainbow from red to blue. And just as a reminder, our red has our long wavelength with our low energy and can be classified as our old dog, whereas blue has our short wavelength and high energy, which is classified as our puppy. And so scientists use this electromagnetic spectrum to classify photons based on their wavelength, and so that they can actually use these tools to explore what happens with our photons from different portions of our spectrum. But let's go back to our light for a second. As I mentioned previously, our light photons are traveling from the sun. They reach our Earth in just merely 8 minutes. What happens when they finally get here? So light photons have traveled from our sun. They're, for instance, reflected off a tree, and they can actually enter a special organ that we have on our bodies called the human eye. And our human eye is uniquely designed to actually detect these photons. This drawing right here is a schematic that you might see in a physiological textbook. This is just a sideways view of the human eye, as you notice here. It's just another way of describing what's going on with our human eye. So these arrows that I've drawn are our light waves. There are photon light particles that are traveling from the sun, reflected off our tree, and actually enter into our eye. And if you were to imagine these small photons entering in, you can imagine them as little particles coming into our eye, right there. So our eyes are very good at detecting photons. How is that so? Well, first off, we have uniquely designed eyes that have special parts called our iris, which is the colored portion of our eye, and our pupil. In certain cases, such as a very dark room, our pupil can actually expand. What's happening is that when our pupil expands, that allows more photons to enter into our eye. You might have seen this with a cat, for instance. A cat's pupils can dilate very rapidly. For instance, this black cat right here is about to perhaps chase a toy, and it wants to collect the most amount of information, the most amount of light before it pounces on that toy. So even the iris and the pupil are uniquely designed to actually detect these photons and change their size in order to allow more photons to enter in. But what happens once the photons actually enter? So at the back of our eye, we have a special series of cells on our retina called rods and cones. And for instance, these right here are our rods. They're specialized cells that are found throughout our body, and rods are just specialized cells to detect light. We also have cones, which are also cone-shaped as well, that help detect light. And scientists have actually used microscopes to look at these and what they look like in real life, instead of just being schematics. And so this is actually a picture of rods and cone cells from the back of a human retina. Unsurprisingly, the rod cells kind of look like rods, and the cones look like cones, which will help you remember which ones are which. So how do these rods and cone cells help us detect light? So the rods are very, very good at detecting photon intensity. They take this colorful picture of our fruit bowl and turn it into a black and white photo, basically, whereas the white portion of our bowl has a high amount of photons. Lots of photons are being reflected off that white portion and entering into our eye, which our rods detect, and it shows up as a very bright area on in our retina. However, some of the darker portions, like the blueberries and the blackberries, show up as dark. They're reflecting less photons, and so they show up darker. So what about color? Our cone cells are very good at detecting color, and they will take this picture of our fruit bowl and change it into its red, green, and blue spectrums. And if you actually blow up, for instance, this red strawberry right here, if you look on our red spectrum picture, it shows up as very, very bright on our red spectrum. Lots of red photons are reflected off our strawberry and are being recorded by our cone cells, which show up as a very bright image on our colored image. And actually what's happening is that we have three special types of cone cells: a blue, a green, and a red, which detect those three types of colors. And all together is what gives us our full spectrum of color. So for instance, you might have seen a red, green, and blue spectrum wheel like this. And if we were to mix them up, we could get the full range of colors as shown in our full color spectrum right here. For a certain portion of the population, they actually exhibit color blindness. What happens in color blindness is that certain colors become muted. For instance, if you exhibit a deficiency in a green cone cell, for instance, this picture of a fruit stand becomes a bit more muted. You might notice it still looks a little green. This is because that the color mixing is affected by the fact that the green color is actually missing. What can happen though, and scientists have developed special glasses which actually can restore sight of these green cone cells so that you can actually go from this picture right here to the colored picture again when you wear these glasses, which just shows how science can actually help and influence these color cones if they don't work as well for a certain portion of the population. So our eyes can detect these colors through the rods and cones that I've mentioned. So the rods can detect the photon intensity, the cones can detect the color. But how do we go from these separated colors back to our original colorful picture of our bowl? So what I haven't mentioned yet is our optic nerve. And our optic nerve is really good at connecting our rods and cone cells to our brain. And it's these series of nerves that connect from our rods and cones and integrate the signal and actually sends the signal to our brain. It will send it through the optic nerve, which is this lit up portion up here, to our visual cortex in our brain. And the visual cortex takes the signals and integrates them all together. So if we go to this picture again, we have our bowl of fruit, we have our 4 separate images, and the visual cortex is what combines these images and allows us to see an integrated picture of our jar of fruit right here. So kind of as a recap of what we've done so far, we've seen light enter our eye, our detector, and then our visual cortex and our optic nerve will integrate that information and will actually send the picture to our brain. But what would happen if instead of a jar of fruit or a bowl of fruit, we had a single photon? Could our eyes even detect a single photon, and would we be able to register in our brain that information that we've seen a single photon? This is a question that puzzled many scientists for many years. To give a little bit of a background, how many photons are actually coming from the sun and entering our eyes every day? So here's our little photon traveling from the sun, hitting our Earth. This is the picture you might see if you look outside. And actually what happens is that 1 billion photons per second are hitting our Earth. This is why you should never look at the sun on a sunny day. That is a lot of photons that can enter your eye and actually damage the cells in your eye. So don't ever look at the sun outside. What about the moon? The moon actually has 1 billion photons that can enter your eye. So we still have a large number. Has many photons that are entering your eye per second. What about our starry sky? Even the starry sky and the faintest star on this sky still has about 1,000 photons that enter your eye per second. So scientists were puzzled. We have to develop a way to actually generate a single photon to even see if our eyes could detect that. So scientists at the University of Berkeley actually wanted to try to do that. They wanted to send single photons into our eye and ask, did you see it? Did you notice anything that happened? So they developed a special photon source that could shoot a single photon at your eye, and then they asked, did you see it? And what do you think happened? Can we actually detect single photons? I don't know. Yes, we can actually detect single photons. The researchers found that given the right conditions of a dark chamber, when your eyes could adjust to the right degree, you could actually see single photons, which just goes to show how well our rods and cones can detect these photons that are coming from our sun. So to kind of summarize, our eyes allow us to observe the world around us. They allow us to see visible light. We can detect color through our cones, and we can even see single photons. Is there anything our eyes can't do? And to answer that question, I'm going to turn over to Alex, and Alex is going to go through a little bit more of the engineering principles and how we can perhaps engineer a better eye.